Teaching an old dog like ping and traceroute a few new VRF tricks. Let's begin. Here are the opt-out questions for this video. So take a moment and go ahead and read through these, and when you're ready, let's begin. One of the concepts regarding implementing a layer 3 VPN is this idea of using the VRF. And it's not just for MPLS layer 3 VPNs. There's other applications for VRFs as well. But one of the challenges is that it takes a little getting used to as far as using our common tools. Things like ping. You think, okay, how tough can ping be? But if we're sitting at R1 and we want to ping Acme at site 1, so we ping 172.16.101.2 and press enter, what's going to happen? You think, well, they're directly connected. It should work, right? And the answer is it's going to fail because this network is not in the global routing table. We need to put a new twist on our ping utility to tell it where to source the ping from. And I don't mean just which interface, but we need to tell it which VRF to go ahead and source the ping from. And if that VRF does have a route to that destination, it will use an interface IP address in that VRF to source the ping from. Other commands that we have to throw the VRF twist on are the show commands. For example, we've been doing tons of show commands with BGP, VPN, v4 routes, and throwing in that VRF quite a bit. So we also have to do it if we want to look at the routing table, for example, for a VRF. So that's another one where it's really easy to forget to throw in the VRF option to look at the VRF related information. IP route, adding a static route. Now, again, that seems like a pretty simple thing to do, adding a static route. IP route, the network, the mask, the next hop. However, when you're doing it for a VRF, we need to include that VRF information so that the router knows, hey, this static route is for VRF Acme or VRF CBT. It's not a static route for the global routing table. Another tool that we might use is SSH or Telnet. And they also require specific instructions to go ahead and source that Telnet session from the VRF for which you want to reach. So if we're on R1 and we want to Telnet to Acme Site 1, we need to include the VRF that we're going to use for that Telnet session. And the same is true if we want R1 to go ahead and Telnet out to Acme Site 2 or CBT2. We need to include the right VRF so we can get to the right destination. And then one last one I'd like to talk about is traceroute. So by default, traceroute is going to be trying to use the global routing table. And if you're on a PE device that has multiple VRFs, unless you tell it that you want to use traceroute in conjunction with one of those VRFs, it's going to try to use the global routing table and very likely not going to succeed to the destination you wanted unless you include that VRF related information. So to have some fun with this, I'm going to go to each of our CE devices and I'm going to open them wide up. I'm going to say, please allow Telnet, no login required in this test lab environment. And that way from R1, if we start using Telnet, we can actually see the prompt of the router that we're connecting to. And that'll verify whether we're going to 192.168.202.2, which is Acme at Site 2, or 192.168.202.2, which is CBT at Site 2. And the same thing goes for Acme at Site 1 and CBT at Site 1. They both have exactly the same IP address. However, they are in separate VRFs, and that's how the router keeps them separate locally. And in multi-protocol BGP, as a VPN v4 route, we've got that route distinguisher that keeps Acme's networks separate from CBT's networks. So even if they're the same IP number, the route distinguisher is going to keep them separate. So let's do a little prep work on our CE devices just to make it very easy to telnet to any one of them. We are going to start on Acme 1 in the top left-hand corner of our topology, that customer edge router. And I'm simply going to go in and go to line VTY 0 through 4. Tell them there's no login required on the VTY lines, and if you do connect, you'll be at privilege level 15. And what I'm going to do is I'm going to do that same treatment for CBT1, and I'm also going to do that same treatment for Acme 2 and CBT2. So I'm not going to make you watch me do the other two because they're exactly the same configuration. So to demonstrate some of the frustration that we might have when working with VRFs, let's see if we do a ping over to 172.16.101.2. And the router's saying, you know what? That is not in my global routing table. The other challenge is we have two interfaces that are both connected to the 172.16.101 network. They're each in separate VRFs, and neither of those are in the global routing table. And that's why the ping failed. So even though R1 is directly connected up to Acme Site 1 and to CBT Site 1, because that route is not in the global routing table, we're out of luck. So we can verify that with a show IP route that'll show everything in the global routing table of R1. And you'll notice we have the loopbacks for R1 through 5. And we have a bunch of subnets for 10 that we're using inside of our service provider network for the connectivity of our routers. But you'll notice there's no 192s, there's no 172.16s. because those are all tucked away in VRFs. Now, if we want to see the routing table for one of our VRFs, let's take a look at Acme. We'll do a show IP route, use the keyword VRF and the VRF routing table that you want to look at. So here it's showing us, this is the routing table for 101 Acme. That's the VRF name. There's the route that we made in our last video that was up on Acme Site 2 that is being advertised over to us through the MPLS Layer 3 VPN. Here's our directly connected network that goes up to Acme at Site 1. Here's the loopback interface on Acme Site 1 that we learned via OSPF from that customer edge router. And the 192.168s are the two networks that we're learning from Acme at Site 2. So the 202 network is the network between R5 and Acme at Site 2. And this 32-bit route is the loopback interface up at Acme Site 2. So what if we needed to add a static route for just this VRF? Now we're going to use the IP route command because that's what we do, but we're going to tag on which VRF it's for. So for example, IP route VRF 101:Acme to get to network 10.10.10 with a 24-bit mask. The next hop is 172.16.101.2, and hopefully that 172.16.101.2 is in that same VRF. Otherwise, it wouldn't be a reachable next hop. So now if we look at that routing table for that VRF, it's going to show us that static route as part of that VRF. So again, just some little tweaks regarding the VRF that we're going to add to some of our common commands and utilities. So a lot of the commands that we're really used to still work, except we need to be conscious and aware that we need to add the VRF related information so it applies, whether it's a show command or a configuration command, so it applies to that VRF. If we want to look at the routing table for our VRF of 102:CBT, we just simply ask for it. And between the two customers, we have some of the same networks. For example, we have this network that's being used with both customers. We also have this network, which is being used by both customers, and this 202 subnet. Over at Site 2 for Acme and for CBT, we're also using that subnet. Let's say that you and I wanted to verify some basic connectivity between our PE device and our customer edge device. If we want to do a ping, we'd have to throw into that mix the VRF for which we're going to do that ping. For example, if we wanted to ping Acme at Site 1, we'd have to say ping VRF, the name of that VRF, then the IP address that we want to ping. Because earlier, when we tried the ping with just 172.16.101.2, because that route is not in our global routing table, and the default routing table is the global routing table if you don't specify a VRF, it failed because the route didn't exist in the global routing table. So the ping to Acme at Site 1 worked. Let's try a ping to CBT at Site 1. Now the funny thing is, look at the IP addresses involved. It's the same exact IP address, but a different VRF. And we have connectivity there as well. And while we're at it, why don't we go ahead and ping the Ethernet interface of Acme Site 2 in the top right of our topology, and also CBT at Site 2, which is in the bottom right of our topology. And we'll just include the VRFs. The IP addresses, again, are identical because both customers are using the same network address spaces. But by including that VRF information, we can use a ping utility and verify connectivity. Now, now I can see the question that might be forming in your mind, thinking, okay, we're doing these pings, but how do we know those are really going to the right devices across the correct VPN? Now, one option could be that we could look at the VPN labels that are involved, the bottom label, look at R5 and look at what R1 has in the VPN v4 routes, and then simply do a trace route to that destination, including the VRF, and it will actually show us whether those labels are being used. And then we say, oh, that's definitely the label for customer X. It's definitely going across that path. Now, for this first trace route, we're simply going up to Acme at Site 1. So we're not, from R1's perspective, we're not going over any MPLS path whatsoever. It's just R1's VRF over to Acme. And the same thing would be true if we did a trace route down to CBT at Site 1. It's just us to them. There's no LSP involved. There's no expected labels. It's simply a direct shot. We're directly connected to that device. However, if we start going over the MPLS network, for example, let's do a trace route up to Acme at Site 2, including that VRF-related information, it'll reveal the labels involved. The top one is the transit label, which is the LSP to reach that next hop, in this case is R5. And 508 is the label that R5 assigned to reach the 192.168.202 network, and I believe that's a /30. And check this out. If we did another trace route to the same IP address, but through a different VRF, for example, 102:CBT, you'll notice that we have the same LSP path, the same path between R1 to R5 across our service provider network. And that's the reason the labels in the first trace match the labels in the second trace. But take a look at the VPN label. We have a different label that R5 assigned to the 192.168.202 network that's part of the VRF called 102:CBT, because they're two separate and distinct networks, even though they happen to have the same 32 bits from an IPv4 perspective. So the key is, when using things like ping and traceroute, we're going to throw in that VRF so that the provider edge router that has those VRFs is going to know which VRF to use to initiate that connection. Now let's say that we wanted to do a telnet session from R1 up to Acme at site 2. Now to do that, we need to tell Telnet, the application, to go ahead and source this from the correct VRF. So to do that, we'll do telnet to the IP address /VRF and then the name of the VRF that we want to use. So that's the secret sauce from a telnet perspective. Use a /VRF. So if we exited out of this and did telnet again to the same IP address, but this time using VRF of 102:CBT, it should whisk us away over to CBT at site 2. And again, if we want to simply verify what is the VPN label in use and what labels are used in the path to get to that next hop, simply using a traceroute with the VRF keyword will source from the right location. Now your customer edges, they are not going to be using any VRF related commands if they're just using normal IPv4 routing. The customers will likely have one global routing table, so they'll just be using ping and telnet and traceroute natively without any VRF references. Now, because a customer may do a traceroute across your MPLS network, you may or may not decide to disable TTL propagation so that this information is not revealed. But in a lab environment where you're learning and practicing, this is a very handy tool to see exactly what's going on. I also should mention that a PC, when it does a ping, it uses an ICMP echo request, and it does the TTL game with that. And a Cisco router is actually using UDP. Now, the reason I mention that is because if you're at the customer edge and you're using, for example, a PC with traceroute, or traceRT as it's called, it's not going to get the information back regarding the labels that were involved in that path. On a Cisco router, a traceroute is going to be using UDP as the transport protocol, and so it's handled differently, and it does have the ability to get back the label information on the path that's being used to the destination. So in short, don't be surprised if your PC isn't giving you the information regarding the labels. But let's say we do something like a ping over to 5.5.5.5, and the replies come back, so we think that's great. Now, the question is, was that label switched, or was it IPv4 routed? Case in point, we could take the middle of our network right here. Here's R3. We'll go into configuration mode. We'll do a no MPLS IP. So we've disabled the label switching path. We'll go back over to R1. We'll simply hit the up arrow. We'll ping again. And, and it had a little hiccup while the network converged. So we'll ping again, and there's our 5 in a row. So if I had given it a few more seconds, it would have fully converged. Now, right now, I can guarantee you that we are not using an LSP to reach from R1 or to R5, because R3 is not participating anymore in MPLS. If we went back to R3, in fact, we have a little message saying, hey, I received some MPLS packets on a non-MPLS enabled interface. We'll enable it again by doing an MPLS IP. So now our LSP is back because R3 is now participating. He was the weak link that was causing it to fail. So if we go back to R1 and we do that ping again, and normally I'd blame that on an ARP request. So let's go ahead and ping again. All right, so now it's functioning. But the question is, how do we know if a ping is actually using an LSP or if it's using IPv4 routing for the entire path? And one tool that we could use to help verify whether or not the LSP is being used in our environment is to use traceroute, but a special version of it. And traceroute MPLS for IPv4, we'll put in the IP address we're trying to reach, the mask, press enter, and it will tell us exactly whether or not it is being label switched across that path. So as we sent the packet out, it had label 209 for R2's benefit. R2 swapped that out with label 310. R3 swapped out that label with 415 for the benefit of R4, and R4 said, oh my goodness, the implicit null, which is that reserved label 3, so it popped off the label, left just the naked IPv4 packet, and it forwarded it onto the final destination. So if we do have issues or problems or challenges with our LSPs, using an MPLS traceroute can assist us in identifying where that weakest link is or where that problem is. Now, in our earlier video titled Implementing MPLS, we created an LSP, a label switch path, between R1 and R5. So 1.1.1.1 and 5.5.5.5. In fact, this one LSP, this one path, everybody's using it. For example, if Acme at site 1, we have Bob, and Bob's trying to reach some resource over here, Bob's traffic is going over that LSP. And Lois over here at CBT Site 1, if she's trying to access some resource over at CBT Site 2, that traffic, that transit traffic, is also going over that LSP. So in MPLS, we have this term called FEC, and it stands for the Forwarding Equivalence Class. And a FEC, or Forwarding Equivalence Class, is a group of IP packets that are all forwarded in the same manner, over the same path, and with that same forwarding treatment, meaning we're not giving prioritization of some traffic over others. So I wanted to bring that up because that's a common term that you might hear. And as we get more into traffic engineering in the more advanced MPLS courses, we'll take a look at creating multiple FECs, and then we can go ahead and put traffic that we want to either prioritize or treat differently onto different FECs so they do get prioritized treatment with something called quality of service, which again we're going to implement by using traffic engineering to force certain types of traffic on certain LSPs. And the job of assigning traffic that's coming in to a specific FEC would be the ingress router. So if we do have multiple LSPs that are going across our network, and we probably have in a production network some redundancy built in as well. So maybe we got an LSP going over this path as well. The person, the entity who decides which FEC you're going to get onto, the ingress router, as this guy is sometimes referred to. So for example, Bob is here and Lois is here. And we're giving some type of preferential or differentiated services to the traffic coming from Acme Site 1. When it comes in, our ingress router right here is going to identify that traffic and then associate that with the correct FEC. And once the traffic gets on a specific path, it's just going to be forwarded to the other side. And some FECs will have higher prioritization than others. And when the traffic reaches the last PE before it goes out to the customer edge again, we call this the egress router from a data plane perspective. So traffic is going in this example from left to right. And the routers in the middle, we could simply call them transit routers or provider routers. So those are some concepts and terms that are commonly referred to when working with MPLS applications like MPLS Layer 3 VPNs. I have had a great time, and I'm so glad that you joined me, not just for this video, but for the entire course. It's been a blast. I've included in the Nugget Lab files the final configuration of R1 through R5 and the 2 customer edges for Acme and the 2 customer edge routers for CBT. So you can refer to those and use those in your practice environments to help assist you with the configuration or to compare what you've configured to what I had from the videos as you lab this up in practice. And as you practice, your skills will improve, and you can use those skills in the production environment to help verify, troubleshoot, and monitor MPLS networks. Now this has been the fundamentals course. And if you love MPLS and you want to progress, additional topics that we're going to be covering in our intermediate and advanced courses would include traffic engineering for QoS, Layer 2 VPNs, concepts such as any transport over MPLS, and VPLS, which stands for Virtual Private LAN Service, overlapping VPNs. For example, maybe you want to have some routes be shared with some sites and not others, or some common routes shared with everybody, but not all the routes. And all of these topics are slated for our intermediate and advanced courses. Now, in preparation for any of those advanced topics, I would strongly recommend that you master everything that we've looked at together in the MPLS fundamentals, because everything you gather now as far as knowledge and skills, we will carry that forward and apply it as we build upon that solid foundation that we're building right now. One other thing, if you like the course and want to let me know about it or let others know about it, I can be reached at Facebook at Keith Barker Networking. That's the most convenient place to reach me if you need to. And I can also be followed on Twitter at Keith Barker CCIE. So once again, I've had a great time, and I'm so glad that you joined me for the videos. I hope this has been informative for you, and I'd like to thank you for viewing.